I guess I got into this just on my own wanting to know, and that wanting to know led me into the sciences and into engineering and then into physics and then into astronomy and meteorology and those kinds of things. So it's kind of a natural curiosity, like, how did this whole thing come about? And it's been a lifelong interest of mine, and astronomy and cosmology are kind of the fields that today answer those kind of questions. So I'd like to start with some disclaimers. The story you're about to hear is true. The names haven't really been changed to protect anybody. But I have 3 disclaimers, and one of those is a personal disclaimer. I mean, I'm only me, and I'm only human, and I have a certain amount of gray matter to bring to anything, and a certain amount of interest. And so I have my limitations in communication, and certainly have my limitations in knowledge. And that's the personal disclaimer. Then there's the humanity disclaimer. The humanity disclaimer is that humans are building pictures of things. That's all we can do in the sciences, is build models in some way or another. It might be a mathematical model or a geographical model, but it is a model. And our understanding is based on these models. And while no one would confuse a map of Greenfield with Greenfield itself, there is a lot of confusion about models that we make, mathematical models, physical models, with the reality itself, which is infinitely complex. Okay? So that's kind of the humanity disclaimer. And the next disclaimer is the disclaimer of science. Science is one way of knowing something. Science makes some assumptions that aren't always clear. And one of those assumptions is that you're separate from everything else, that you're outside of it. Things can be broken up into subject and object, and you can study the object impassionately. And science has brought us to some really wonderful places and some great understandings. But it's not the only way of knowing. So we have to keep that in mind, that we'll present a viewpoint here. And though it's the truth, truth not with a capital T, but truth in it's the best we know right now. Okay? That's a truth. It's the best we know right now, not truth from truth and lie, or truth with a capital T, because you'll never know the capital T. We're very limited human beings. We're in an infinitely complex universe. There's a lot to know out there. You're never going to know it all, and you're never going to get it right. And so science is a creative endeavor that takes one from a place where you're at and shoots down the old models and creates newer models. And this will always happen in the sciences. There'll always be a better explanation, a more complete explanation. So science is a very creative human endeavor that is interesting as can be. Okay, so let's start. There was a time before time. There was a place before space. The way we understand the universe right now is that 15 billion years ago, there was nothing. No space, no time, non-existent. Not that there was no matter in some empty space and time was just marching on. No, not that at all. There was non-existence, emptiness, nothing, 15 billion years ago. And then a spark, a creative spark of energy appeared. And in that energy contained space and the characteristics of space, contained time that could proceed on. In that spark of energy was the potential for everything that now exists and will exist. And since that time, this space has been expanding outwards and carrying everything outwards with it. It's been carrying matter, it's been carrying energy. Who knows what else it's been carrying, but it's certainly been carrying those 2 things outward. A lot happened in the first fractions of a second after the Big Bang. That Big Bang, as it's called, was an event that happened once, as far as we know, that created this universe. Does that mean there are other universes? We don't know. But we know that this is a universe, uni meaning one thing. We all came from that one thing. And that story, the history of everything, is a story of development and of evolution on many different levels over the last 15 billion years. The first few seconds were involved only with light, photonic energy and radiation that was so strong and so intense that even matter couldn't exist. If you can think about a light so bright and so strong in such a tight space that not even atoms or the nuclei of atoms could exist, that was the conditions at the time of the Big Bang. From then on, as space expanded, the energy that was part of that creation expanded with it and cooled down. Once it could cool down enough, the nuclei of atoms could form, or quarks, the particles that make up neutrons and protons, they could form. And from some point in time, a few seconds after the Big Bang, all that existed was quark soup. Just this intense energy and matter condensed as energy. Well, we now know that matter is just condensed energy. That's all it is, energy that's gotten localized in some particular place in some particular time. We call it matter, but it's energy, energy in another form. It took Albert Einstein to tell us that in 1905. So as this energy expands, time and space expands with it, the energy cools down, and quarks can then form themselves into neutrons and protons. And now we have a period of time where the only thing that exists is the elementary particles, primarily neutrons. Neutrons are little neutral particles of matter that are in the nucleus of every atom. And with the continued expansion, those neutrons could decay, some of them, into protons and electrons. And now we've got a mix of protons, electrons, and neutrons, still annihilating and rebirthing each other in this process of energy that was going on. And at some later time, atoms could exist without being blown apart by the energy that was present. And so the neutrons and the protons kind of gathered together. Electrons formed orbits around the protons. I'll talk of these as particles, but we know that they're not particles. They're probably standing waves of energy condensed in space, but we'll talk about them like they have particle properties anyway, because they do have some particle properties. So now we have atoms, and that took about an hour. 1 hour after the Big Bang, space had expanded enough, energy had cooled down enough to let atoms happen. And those atoms formed only two things, hydrogen and helium. So if you were in a chemistry class, the periodic table would be a cinch. 2 squares instead of the 100 that we've got now. And in that time of atoms, there developed, as space expanded, a series of astronomical objects called quasars. Those were the first objects formed. We believe quasars to be gigantic black holes that are involved in sucking up the spare matter around it, held together by a force called gravity. And I have to say this about astronomy. This is where astronomy gets you into history. When you take a telescope and you look out in the sky, you are seeing the light coming to us from objects that existed a long time ago. Because light, we know, travels at a certain velocity, a certain speed. So therefore, whatever happened out at star XYZ, it's taken that light a long time to get from there to here. So the further I can look out into the sky, the more I'm looking back in time. So the telescope is a time machine it allows one to look back and to see how things were. And when we look way, way back, all we see back there are quasars. So we know that they were the first things formed. And it's taken just till the last 30 years for humankind to be able to look back that far in time with our telescopes to see what's out there. After quasars formed, there was a period of relative darkness that had to last probably a couple of billion years until another process could happen. And that other process was the coming together of matter, again attracted by gravity, in the form of units that we call galaxies. Now, a galaxy is a large, would take light 100,000 years to go from one side of a galaxy to another. That's how big these are. But these galaxies, early galaxies, formed, and the formation of these galaxies, we'll see some pictures of them on the slides, also led to the condensing of hydrogen in smaller groups, which would fire up by a process of nuclear fusion and become stars. So stars are an important thing for us because they were the first thing that relit the universe after the Big Bang. There was this flash of light, of photonic energy at the Big Bang. Then there was darkness for a long time. And then there was light again as the hydrogen fusion reaction processes inside of stars came to being, came to light, started to generate energy in the form of heat and light. Now it's pretty amazing that we know presently how stars work. We know that the only thing that matters about a star is its original mass. We know that all stars are made up of the same thing, hydrogen, 75%, helium, 25%, because that's the building matter of the universe. That's what was there from the Big Bang. So where do all these chemicals come from that we find around us? Well, the fusion process in stars takes two hydrogen atoms. It's a little more complicated than this, but I'll simplify it. Takes two hydrogen atoms and through a process of nuclear fusion squishes them together and creates a helium atom. Also, in that creation process, a lot of energy is released. Some of the energy from the Big Bang is given back through the process of hydrogen fusion. And that light is then sent out, and we today can go out and look at the sky at night and see all of these hydrogen fusion reactions going on in stars. Now, helium, if a star is big enough, its gravitational force will bring some heliums together and squish them together hard enough so that another fusion process will happen. And that fusion process will make carbon. And carbon's a good thing to have. Our bodies are made out of most of it, besides hydrogen and oxygen. And it doesn't stop there. If a star is even big enough, once it's used up its hydrogen fuel, it will contract, build up a lot more pressure, and fuse carbons together. And so we can build the periodic table all the way up to iron, getting energy at each fusion process. Okay? At iron, it stops. Yes, question?
Does that go down the periodic table, like, by the numbers?
Yes, it does, by the numbers, right down the periodic table, until you get to iron. Iron is the stop of the process, and once a star has converted all of its original hydrogen into iron, it's done for. And its process from then on, well, it can go one of like 3 or 4 different ways, but we'll talk about that later. So where do all of the heavier elements come from, the ones beyond iron in the periodic table? They have to have been built somewhere. And there is one process that builds those heavier elements, And that is, if you have a very massive star and it uses up all of its energy, it goes through what's called a supernova explosion. Well, it really should be called a supernova implosion, because what keeps a star the size it is a balance of two forces. One is gravity, which pulls everything together, which is holding you to the ground right now. Any two masses will be attracted to each other by a force of gravity that you're feeling. I mean, I'm not floating up in the air, thank goodness. That's gravity working on me. So that's one of the forces that tries to pull all the hydrogen together to make a star. The other force is the force of radiation pressure pushing outwards. And the size of any star will be a balance between these two forces. And as long as the star is producing energy, through fusion, combining the chemicals that it has, then this size balance works well. But once those nuclear fusions shut down, once it's converted all of its hydrogen into iron, there's no energy pushing out. And so you get a tremendous collapse. All of the matter in a star shooting inwards to the center. And when that happens, whatever that star had made, it becomes condensed so much that atoms can't exist anymore. Electrons get smooshed into the nucleus. It all becomes one giant nucleus, and then turns around and explodes and scatters everything outwards. And we see pictures of this going on now for stars that have gone supernova. So that supernova explosion produces everything in a periodic table. It fills it, okay? And that dust from that explosion is scattered into space. Now, thankfully for us, that dust recombines with hydrogen that's in space from the Big Bang, and second-generation stars form. We are a second-generation solar system. Our solar system is the remnants of a supernova explosion that happened probably 5 billion years ago, somewhere in this locale. We're not sure which star it was. There are some traditions in Africa, the Dogon people, that identify it as Sirius B. And for an illiterate 2,000-year-old tradition of a star called Sirius B that's not even visible by the naked eye, to be called their seed star that created this solar system is pretty interesting. And I would love to know if that's true or not. But there's a tradition by the Dogon people in West Africa that Sirius B is the seed star that created us. That comes from a different way of knowing. It may be true, it may not be true. I don't know. But there are other ways of knowing, and I'll talk about them at another point later on. So at some point in time, roughly 5 billion years ago, the remnants of this supernova mixed with the hydrogen gas that was presently there in this area of space, and this cloud started condensing, again by gravity. Gravity is the big force that makes everything work in astronomy. It's a force of attraction. It brings things together. So this cloud started coming together, and most clouds in space have some sort of angular momentum. They're moving sideways as well as linearly. And this cloud ended up, by the force of gravity, coming together and spinning rather rapidly around and formed a disk of material with most of the material at the middle. Well, this is our proto-solar system. This is the start of our solar system. And then through this process of coming together, the sun at some point had enough mass to ignite its furnaces again, and the planets condensed in their little areas of space. And this process probably took 500 million years to happen, that the planets all formed. Now, astronomers use the word accretion to show that little pieces are joining together. And this was not a very peaceful time, because if you can imagine pieces floating around in space the size of the moon deciding to join each other, really colliding, and the forces of collision and the energies involved, so fantastic that everything was molten, totally molten. Incredible energies, plus the fact that the leftover remnants of that supernova explosion, most of them were radioactive isotopes. And radioactivity itself is a heat-generating kind of thing. So all of the atoms that came together to form the planets came together largely radioactive, with a lot of internal heat, and came together with the heat of accretion from this fantastic bombardment. Just take a telescope and look at the moon, and you get an idea of what that bombardment was like. I mean, this was humongous. And even after the planets formed, even after Mercury, Venus, etc. formed, there were tremendous collisions, just tremendous things. Our moon, for instance, came from a collision of a Mars-sized planet with Earth. The presently accepted theory, based on the data we've gotten from the moon in the last 20 years, is that a Mars-sized planet and Earth collided in Earth's orbit. That Mars-sized planet hit the Earth, which had a little bit of a solidified crust, blew a bunch of that crust up into space. The center of this planetesimal then circled and joined with Earth and molded to become part of the molten Earth, and the material blown off the surface of the Earth condensed in orbit to form the moon. So our moon was caused by a fairly large hit on the planet that happened sometime after the Earth formed and cooled a little bit, because most of the moon is made of rock. It's light material. Its density is low. We know that it came from the surface of the Earth. We have dated it. We know that it is Earth material that it's made out of. Okay? Mercury, the innermost planet that buzzes around the sun very rapidly, it got hit with something so big that it like fractured the planet. It created this calorous basin on Mercury on one side where it got hit, and completely jumbled the crust on the opposite side of the planet from the seismic shock going through the planet itself. So we know Mercury had a very violent beginning. All these planets having formed from this original disk of whirling matter all go around the sun in the same direction, and they should all be spinning on their axis the same way that Earth is spinning on its axis. But three of the planets don't. Three of the planets, Venus, got belted with some big object during its formation, which knocked it off kilter. And Uranus as well got totally knocked on its side. It should be spinning like this. It is spinning like this as it moves along in its orbit. So, you know, that early period was really disastrous. I mean, it was very violent. It was a very violent beginning to our whole solar system. And we've seen remnants of this kind of thing happening. We know pretty well for sure that Earth is under regular bombardment. I mean, Deep Impact is not totally science fiction. 65 million years ago, Deep Impact created a basin in the Yucatan Peninsula, threw enough garbage into the air to make 95% of the animals on the planet die, and plant life, completely shrouded the planet in dust for years and years and years, wiped out the dinosaurs, left a nice little niche for our ancestors to survive in. So that was a good thing. But this kind of thing happens all the time. We just saw in 94, 95, the Shoemaker-Levy comet impact on Jupiter. And that was the first time we got to really see an impact in process. You know, this planet getting bombarded from the outside with these objects come plowing into it. So it's a pretty scary place. And the formation processes of accretion were very violent to begin with. Let's pick our story up, though, on planet Earth. Earth has a long history. 4.5 billion years ago, this formation started. And about 4 billion years ago, the atmosphere formed. That is, things were cool enough now. Now, how fast a planet cools depends on its size. So the bigger the planet, the hotter it's going to be. Still now. I mean, Earth is still a molten ball. You know, you dig under the crust 10 or 20 miles and you're in molten magma, right? That's what volcanoes do. They poke their head up through the crust and, you know, let us see what's down under there. And underneath that is molten iron. So Earth is largely got its original energies with it. It's still very, very hot inside. But it cooled on the outside, and the cooling happens by radiation into space. The reason we, yeah, question?
Are there other masses that are cooler and smaller?
Yeah, take the moon and take Mercury. They are both very cool and no internal heat that we can measure. The heat that they get is the heat from the sun. Almost all the other planets are net heat losers. That is, they are losing more energy every day than they get from the sun. And where's that heat coming from? Their energy of formation that's still there. There's still these, even after 5 billion years, there's still these molten drops in the sky, basically, with a little slag on the outside that we walk around on called crust and earth and rock. And it really is. It's slag on the outside. The lighter elements that have floated to the top, the heavier elements that have gone to the bottom through the process of differentiation, which is a normal step in a planet's formation. So the core gets heavier, the top gets lighter, and rocks are light, and water is light, thank goodness. So we're up where the water is, which is good. You wouldn't want to be down below. Now, at about 4 billion years ago, Earth was cool enough to have liquid water on its crust. And that's really important because the first atmosphere on Earth was primarily carbon dioxide, much like Venus is right now. Pretty pure carbon dioxide, a few other things, but mostly carbon dioxide. And that carbon dioxide would have stayed, and Earth would have stayed a totally lifeless planet like Venus is, except for the fact that life was starting to develop. The oldest little fossil kind of thing that we can find is 3.5 billion years old. So after the Earth cooled at about 4 billion years ago, it only took 500 million years for the first kind of self-replicating life to develop. And that was a life that lived on carbon dioxide in the ocean. And thank God for, as far as we're concerned, those little plants were capable of taking carbon dioxide out of the ocean and building little shells for themselves, protection, armor for themselves. And over billions of years, they doing that, taking the CO2 out of the ocean, took the CO2 out of the air. So carbon dioxide from the air goes into solution in the ocean. Then these little life forms tie up that carbon dioxide. They die. That carbon dioxide is turned to calcium carbonate, for those of you who have chemistry. That drops to the ocean floor as sediment. And gradually, the amount of carbon dioxide in the Earth's atmosphere drops and drops and drops, which is a good thing. Carbon dioxide is not good to have around. So about 3.4 billion years ago, this process of tying up carbon dioxide was fairly well along, and it took billions of years to take that carbon dioxide out of the atmosphere. In the meantime, the first kind of plant life is starting to produce oxygen as a byproduct. It's taking in carbon dioxide, photosynthesizing, and it's putting out oxygen. So we have two things going on, carbon being taken out and oxygen being increasing in the atmosphere. Okay, those two processes are going on. What about 1 billion years ago, the process of sexual reproduction started. And this is an important adjustment into the evolution of life, because sexual reproduction means there's a mixing of genes and creates divergence. And it's kind of neat, the balances that are around. I mean, life really needs to reproduce itself true to form, because life is a very complex thing. And the DNA helps us do that. But at the same time, conditions change on the planet. And those life forms that have certain characteristics that are better adjusted to that environment on the planet, well, that will lead to survival. And so this mix of mutation and reproducing true to type, these two things are kind of in balance with each other, these two different forces, needing to do new things yet needing to keep the old true to type and true to form. And this process is still going on today. So at 750 million years ago, we have the first multicellular fossils are found. That means we've got specialization of cells happening within the particular life forms. And first life appears about 400 million years ago on land. So until then, we've got barren land. 400 million years ago, we've got one continent, Pangaea. It's all together. We've got a lot of water over the planet. We've got an oxygen-rich atmosphere. We've got fishes swimming in the ocean. And we've got the first life starting to move out onto land, and that's plant life. And this plant life on the land is also a helper. It's taking in CO2 and releasing oxygen. And we find the first plants that have seeds starting 345 million years ago. 340 million years ago, it's the time of lungfish. I didn't see the play. Wrong Turn at Lungfish. That's what that was about. The lungfish was a fish that learned to breathe rather than taking oxygen from water. It was taking it from the air to be able to move from pool to pool as things dried up and climates changed and glaciers came and went and the continents slipped around many times on this liquid molten ball, so that it was just moving around a lot. Okay, 200 million years ago, the continents separate. They start to separate, and plate tectonics start. Very recent in astronomical terms that this should happen, but it did happen 200 million years ago, that South America split off from Africa and North America split off, went its own way with its own little plate. Yeah?
Why?
Why? Apparently convective forces from the inside of the Earth drive the plates. That we know that the Earth is molten on the inside and it's losing energy out. So that means there's a heat transfer process by convection. And it's this convection thing that develops cracks in the top and spits out volcanoes. But it's a convection process that's moving these plates that are floating on this crust around, that's driving it all. And it doesn't drive it very much, maybe an inch a year or something like that. But let there be a place where those plates don't slide by each other and that pressure keeps building up and building up. I mean, we can now instrument this. Geologists can instrument this and know when the pressure is building up and know when to expect an earthquake when it finally slips and moves a foot and shakes everything up on top of it. But it's convective currents in the magma that are believed to drive the plates. And it started because the crust got thicker as the Earth gets cooler. There's some process in there, the thickening of the crust as the Earth cools, that then started driving this continent apart. It may also have been an imbalance in the weight, too. You know what it's like in your washing machine when the heavy rug gets on one side and the thing goes thump, 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 thump? Okay, that kind of a process. An imbalance on the surface that drove the continents apart because they were all grouped in one particular place.
So it happened to any similar planet?
We have not observed plate tectonics on any other planet in our solar system. Just Earth. And we're curious about that. We scientists are curious about that. Okay. At this point in time, when the continents separate, the reptiles are dominating. It's the age of the dinosaur. And we find the first mammalian reptiles, first mammal reptiles. Yes?
What accounts for the nitrogen in the atmosphere?
Nitrogen is inert, and it was there to begin with, and it doesn't react with very much. It's fairly inert. It reacts with ammonia. It probably also splits up methane. Ultraviolet light from the sun, before the ozone layer got up there to protect Earth, will disassociate a lot of atoms. Venus lost its water this way. H2O exposed to ultraviolet light splits off the hydrogen then drifts off into outer space, and you're left with oxygen that gets tied up in rocks. So there is a dissociative process of the lighter molecules by exposure to ultraviolet light. And methane, NH3, ammonia, NH4, I'm not quite remember all my chemistry, but those nitrogen-hydrogen compounds can also get disassociated by sunlight, and the hydrogen then leave, and the nitrogen then be left. So there's a couple of explanations for that. Okay. Thank you for the question. First flowers 100 million years ago. Pretty recent, out of a 5 billion year history. 65 million years ago, most of the large reptiles totally vanish. And again, we believe a comet strike did that. We believe we've located where it is, and we believe we have the evidence for that. And any of you have questions, I can comment on that a little further, but let's just keep going here. 30 million years ago, we find a humanoid lineage beginning. So we're very recent additions to the planet. It's been around a long time before us. Now, if there was nobody there to see it, was it really there? Well, that's a philosophical question that I think the answer is yes, but there is something to this observer thing. I'd like to do a few slides and talk about a few other things dealing with astronomy here. So let me see if I can figure this all out. What did I do with the remote? Okay. All right. If you were to look out in the direction of our galaxy is the Milky Way. It is a galaxy of maybe 100 trillion suns like ours. It takes light about 150,000 years to go from one side of the other. We are out on a spiral arm, as we'll see some pictures of spiral arm galaxies. Anybody's way here? Just lost my mic. We are out on a spiral arm, and if you could look very clearly at night, this is what you would see looking in the plane of the Milky Way, our galaxy. It's a busy place. This is what it would look like if you had eyes that could see very special things. Our eyes are matched. I guess I should talk about this. Our eyes are matched to the output of our sun. Our ancestors survived by being able to find food and avoid saber-toothed tigers. And that required seeing by the reflecting light of the sun. So we have eyes very perfectly attuned to the sunlight, the light from our sun. If we had a different sun, we'd have different eyes. Our eyes would have evolved differently. Our blood is a seawater solution at the salinity of the sea, as it was at the time when our ancestors crawled out of the ocean. We are a packaged seawater system. That's why blood is salty, and you can measure the amount of salt in human blood. And since the salt in the ocean started at 0 and is gradually building up with time as the rivers wash more salt off the land into the ocean, you can tell exactly when our ancestors made this little trip from a water-based environment. And I guess you can pretty well, so we weren't deposited here by UFOs, for those who might believe in that. We are a life form, a continuation of a life form that's evolved here on planet Earth, and there's a lot of proof of that. You may believe something else, but there's a lot of proof to the fact that we evolved here, and I just gave you two things that match, that show that we are, besides the fact that our DNA is a 99% match to a very common line of DNAs that comes up with other animal types as well as ourselves. So if you had eyes that could see at radio frequencies, this is what you would see looking at the sky at our Milky Way galaxy. If you had eyes that could see just hydrogen, this is what you would see looking at our Milky Way galaxy. That's where the hydrogen is. If you had eyes that could see, and the little blank spots are shadings, they're not real. If you had eyes that could see at microwave frequencies, that's what the sky would look like. If you had eyes like Superman with X-ray vision, this is what an X-ray picture of the sky looks like. And again, the black marks are just antenna marks. This is what it looks like for gamma rays, light that's much, much higher in frequency than our eye can see, that are produced by nuclear reaction processes in stars. Another shot of what gamma rays look like, where the bright spots are. Now, if we could go outside of our galaxy and look back at it, we would see that the sun was located 2/3 of the way out on a spiral arm, and our galaxy is a disc kind of shape. It's in a plane, like most things are that came together out of a rotating cloud. And those bright spots are globular clusters, as they are called. And here's a picture of a galaxy cluster, a cluster of galaxies, 4 galaxies in the constellation Leo. Lots of galaxies around. Each galaxy, hundreds of trillions of stars. So we're talking about a big place. Now that little red dot is supernova 1987. That is a supernova that exploded. It showed its light for a few years, and now it's blowing its dust out in the surrounding space, much like the supernova did that created the material that you and I are made out of. This is an example of a barred spiral galaxy. It's a type of galaxy with 2 main arms. This is called the starburst galaxy. Some of this is really beautiful stuff, and astronomy has inspired a lot of artists and paintings and that kind of thing. This is what's called the antenna galaxy. Lots of star formation, stars presently being made. Stars live their own life. A star like our sun that's very small will live for a long time. It's probably half used up. It'll probably live for 10 billion years. A star that's a lot more massive than our sun won't even live for 1 million years. It's gonzo. So Earth finds itself in a just right place, next to a just right star at the just right distance away, with a just right moon that made tides to wash water by, so life could have nutrients brought to it and waste taken away, at just the right temperature, just the right chemicals. Okay, here's an example of different types of galaxies, since we're talking about galaxies. I was showing you quasars, but we can't quite see quasars. They're too far. We know they're there, and we can look at their spectrum, but we can't get pictures of them. So that's what the different galaxy types look like. There's elliptical galaxies and spirals and barred spirals and irregulars, etc. This is a galaxy with a couple of companion galaxies. This happens to be the M100 galaxy, as it's called.
Each
Whoops.
of those have trillions of stars.
Each of those have hundreds of trillions of stars.
And when you look at that picture, you see what look to be stars on the periphery. Are those other galaxies?
Probably so. Other galaxies, right. All of most, well, I won't say all, but when we look out at night at the sky, everything you're seeing is in our galaxy. If you're going to see something beyond this galaxy, you need a telescope, a good-sized telescope. Then you can see these kind of things. But like this M100, it's not visible to the naked eye. Okay, there's only 2 galaxies that on a really clear night you might be able to make out. Everything else is in our Milky Way galaxy. Because the farther away, the dimmer it's going to be. And so, and there's a lot of distance between galaxies. So, it's it's a lot of distance between stars. The closest star is like 4 million light years from us. So that's a long way if you had to walk. This is another shot of a galaxy in M100, an irregular galaxy. This is the Sculptor Group galaxy. Yeah, typically 400 trillion stars. We don't know how many planets. Yeah, thank you. We think that there's a lot of planets. We think we're typical. But so far, we've only found 21 planets that are not connected with our solar system. But they're very hard to see. Planets don't shine by their own light. They reflect their sun's light, and that makes them extremely hard to see far away because you're looking into the glare of its sun, besides the fact that it's really dim. So we have to use various techniques for detecting planets, and so far we're sure of 21 of them. These are 2 other Messier objects, M16 and 17. They are nebulae. That is, they are gas in space that's being activated by the bright light from a star. Okay, there's the great Andromeda Galaxy, which is our companion, our closest galaxy. There's the Sombrero Galaxy. Looks like a sombrero, doesn't it? Here we go into the Trifid Nebula. Beautiful, exploding gas moving through space, being lit by stars. The Ring Nebula, let's see where that one got its name. Another shot of the Trifid Nebula. A star cloud in Sagittarius where new stars are forming. The Bridal Veil Nebula. Really pretty, aren't they? Horsehead Nebula. See where that one comes from. Okay, now we're getting closer to Earth. I've taken us out from the far out galaxies and we're moving in. This is the best picture we have of Pluto and its moon Charon, taken from the Hubble Space Telescope. This is what an asteroid looks like floating in space. One of our spacecraft went right by this and took a snapshot, sent it back to us. It's the asteroid Gaspar. We come in on Neptune, a big icy planet way out there. And Uranus, another icy planet, mostly gas. And one of its moons that's been, Miranda, that's been blown apart and recondensed several times, been hit, smashed to smithereens, and it hasn't quite come together, has it? It's just like pieces jumbled together. You can see what's happened to it. Of course, you all recognize that. This lovely Saturn, one of the prettiest things in the universe, at least in our solar system. Close-up of the rings of Saturn with some little moons that keep the rings in shape, called shepherding moons. Those little moons there are what keeps Saturn's rings all together. As we come a little closer, we get a shot of Jupiter. Another shot of Jupiter. Jupiter would be a great planet to study weather on because its weather is fairly predictable. That cyclone or hurricane, Great Red Spot, has been there for 300 years, as long as we've been observing it and recording it. So talk about a long-lasting hurricane. Close-up of the Great Red Spot, or the eye of Jupiter. One of a group shot. They're obviously never together like this. Yeah.
And the last shot, the eye of Jupiter,
Yeah.
that's not on the surface, is that?
That is in the upper atmosphere. It is a weather system. There is no surface to Jupiter. Jupiter is a liquid hydrogen primarily, so if you went to stand there, you'd sink. You can't stand there. Don't plan on landing on Jupiter. Mostly a gaseous outer layer, which is what we see, and differentiated, layered, of four different gases, which I forget the names of, but I could look them up. But the moons of Jupiter, they're really interesting. They are hard. They are solid, rocky kinds of things. Here's the group portrait. And they're very different. All the moons are very, very different. This one is Callisto, kind of looks like our moon, very pockmarked. This one is Io, very volcanic, presently very active volcanoes. We sent a spaceship by it, and while the spaceship was going over it, a volcano blew off. We could watch it and take shots of it. And this one, oh, this is a shot of Mars. All right, this is a close-up shot of Mars as we work our way in. Polar ice caps, you can see. Red because there's a lot of iron oxide in the soil. Basically a desert planet. Mars again, very high mountain, Olympus Mons on Mars. Now we come to home. The only planet in the solar system with a lot of water, just the right distance, just the right temperature. Beautiful planet, little blue marble hanging in the sky. Let's keep it that way. Another shot of Earth. Of course, our moon showing its pockmarks where it's been hit by meteors. Another shot of the moon. So we're moving inward. Venus. Very thick, dense atmosphere, super hot. Another shot of Venus if you could see through the clouds. Hot desert. And Mercury, very pockmarked. Looks like our moon. Clobbered. And of course, the thing that keeps it all alive, our sun.
What kind of picture is that?
That's a picture in the ultraviolet. Yeah, that's a picture in the ultraviolet. And that's what it's like. It's a massive explosion that, thank God, has been going for 5 billion years at a very steady pace and is keeping us toasty warm. We live on packaged sunlight. The food that you consume in the cafeteria brings you carbohydrates, which is stored sunlight energy. We heat our homes on packaged sunlight, coal, oil, wood, whatever it is. The sun is the energy source of our life and our solar system. It's what's keeping us going. Okay. Any questions, things that have come along? And I'd like to wrap it up in a few minutes. I got about 4 minutes, I guess. All right. I'd like to say that, and share a couple of things. What you've seen and what I've talked about is evidence from the sciences. Evidence from human senses being extended outwards through telescopes. You can look at the progression of life and the development of life on this planet as a totally random event, happened all by chance, and you can hold that opinion. Or you could have an opposite opinion that everything that's happened has been just right to lead us where we are today and to give us life and let us be there. You can look at humanity as a destroyer of nature and as an evil force, a cancer on the planet. Or you can look at humanity as the planet itself becoming conscious and now wanting to preserve life as it exists. Different seeds, wanting to cultivate different varieties of flowers, wanting to protect the planet and keep asteroids away. Humanity may very well be Earth incarnate, that Earth will carry Earth and life that's developed here out into the solar system. So if something happens to Earth, so a space program is really important. You know, if something happens to Earth, life, we have to carry life with us. We live on life. I mean, the bacteria that is in our intestines is the bacteria that's been around here on the planet. You know, we are a carrier of life. Just to live, we have to carry it with us. So wherever we go, we're going to take life with us. We bring some other things. We bring thought. We bring awareness. We bring the noosphere. We bring the ability to comprehend. And that's important, because when you start talking about purpose and what can we say about purpose from all of this, and we can say some general things, that there is a positive energy at work in this universe that has produced us and all the life we see around us. You can call that God, you can call that the universe, you can call it what you want, whatever name you want to give it. But it's there, and it's been changing, and it's been at work behind the scenes. And it can be tapped into. That energy and that knowledge can be tapped into. We bring spiritual values. We bring a very different ethics. We bring a concern for the individual. Nature is very concerned about the individual. It's the survival of a species that nature works around. We bring a new value, a new order to things. Science doesn't talk about glory and love and those kind of things, but we do. We bring that. That doesn't come out of the hard science. That comes out of inner values and our ethics and our morals and what we feel is right and what we do in our life. T.S. Eliot wrote, "We must not cease from exploration, and the end of all our exploring will be to arrive where we began and to know the place for the first time." So it's a knowing. Life has a purpose of knowing in it, as well as having a purpose of developing, of creativity. Nature is very creative. Everything gets tried, and humankind is very creative. And we take part in that creation process. We are co-creators with nature or with the divine in this physical universe. We have artists in our midst. We have people that build buildings. We have everybody. You know, everybody has a place to be creative, has a unique gift, something to bring. There are people who tune in to something beyond themselves and know things that the rest of us can't know by sciences. Albert Einstein was one. I mean, he could tune into something and come up with ideas that was totally brand new, and we're still working on proving him wrong. We haven't been able to. The last thing I want to say is that there are other people, there are poets and mystics and writers that tune into things. Science fiction leads science. That there are other ways of knowing besides science. Science is a good way. It's a good way to share, and it's brought us a long way. But there are other ways of knowing. I mean, what I've shown you today is all in the last 100 years. Just in the last 100 years that we've been able to really say all of this. So I'd like to share a poem that was written in 1270. 1270. Before telescopes, before Big Bang theories, before nuclear reactions were known, before galaxies were known, before atom and the motion of electrons in atoms were known. 1,000,000 galaxies are a little foam on that shoreless sea. We came whirling out of nothing, scattering stars like dust. The stars made a circle, and in the middle we dance. Every atom turns bewildered, and it is only God circling himself. 1270. He's got the Big Bang Theory, understands galaxies, understands atoms, and understands that it's we that were there at the beginning. Why shouldn't we know this stuff? We were there. Every atom in your body is starlight. You were there as a consciousness, or certainly as a material, at the least as a potential. You were there. So this history is your story. It's how you got to be.